Coming to implementation plan, the simulation of the smart farming system was done in Kuja simulator. Sky modes in Kuja is used to emulate T mode sky modes. T mode sky mode has provision for temperature, humidity, and light sensor simulations, and we require these sensor information in our application. To study the communication of the modes in sensor network, we use 15 sky modes, in which mode number 1 is the center or the sync mode. Here in the picture, we see a figure that shows how we plan to place the modes in the field in concentric circles. The sync mode is 1 seen at the center, and if mode 9 wants to communicate to 1, it can hop to 3 to reach 1. Then coming to the application and simulation, we developed two applications in order to study the communication uh, of wireless sensor networks built on Contiki. Smart farming application 1. This is a basic application that we developed for smart farming. The shutter in this farming system is centralized. That is, only the central mode controls the activity of the shutter. In our code, we have a single protothread that we called as smart farming process. Its function is to generate random values for temperature, humidity, and light sensors, and detect if it goes beyond some optimum value. And in case uh, any of the modes detect a value that is more than the optimum value, it sends a flag to the central mode, informing that at this certain mode, the current condition is adverse. To implement this, we use the collect function that is already available in Contiki examples. The function transmits data from every mode to the collect sync mode, which is the central mode here. In our application, if either temperature, humidity, or light intensity goes beyond the threshold, the shutter is closed. These thresholds are set as: for temperature, it is 30 degrees centigrade, humidity 95 percentage, and light intensity is 90 units of lux. In order to open the shutter, all of them should again come back to optimum value. Okay, smart farming application 1 is a typical case where farmers want a long life for the modes, because the data transmission of each mode is done only in case adverse conditions detected. There is not periodic data transmission from each of the modes. Also, our duty cycling method for the radio is very good at conserving energy, uh, and it well fits for this application. Another farming application is the smart farming application system 2. This can be used for scientific purposes to learn the behavior of a field. In this application, the SIG mode keeps collecting data from all the modes periodically. Unlike the first system where individual modes detect the adverse condition, in this case, the SIG mode verifies if the data acquired is more than the permitted threshold. If it is more than that threshold, it signals the respective modes to close its shutter. We have a decentralized shutter system here. So each of the modes are signaled again by the central mode to close the shutter. So we can see a two-way communication. From the modes to the central mode, it detects and it communicates back to the end mode, telling it to either open or close the shutter. The data from each of the modes is sent periodically to the central mode, resulting in high traffic in the network. This leads to more energy consumption of the modes. Uh, as implementation of the code, same as before, we have used a protothread, the smart farming process, with the collect function to periodically send these information to the sync mode. The sync mode checks data from all modes. If it's more than the threshold, the sync mode invokes another process that is called the shutter process. The shutter process is invoked only when there is data to be transmitted back. That is only when it has to say either open or close the shutter. Only in certain conditions. It floods the whole network. It uses this trickle function that is also available in Contiki examples. As already mentioned, this is very less energy efficient as each of the modes periodically transmit data. Uh, this is the trade-off that we use that we have to go through in order to study the condition of the field. Both these applications were tested with 20 modes, and it's scalable. um, and the scalability depends mainly on the memory available in the central mode. Now going on to the simulation. Before I start with the simulation, I would like to show in Contiki where we set the protocol stack. So our platform is Sky Mode, and in Sky Mode, if you go to the Contiki configuration file, we have made it as CSMA driver, and for radio recycling, we use Contiki Mac driver for high efficient energy efficiency. Our program has been stored in the examples folder, smart farming application 1 and 2. Let's open up the Kuja simulator to simulate our network in it. We start a new simulation, and we add sky modes to it. We already have this is our code smart farming C within the smart farming application 1 folder. We already have simulated it. A .sky file is available. We create for because of limitation of time, we are not simulating 15 modes. We will just show 5 modes. Let's assume this is in the center. Let's start. If the LED is bright, it means that the shutter is closed. The centralized shutter in application 1 is closed. If it is dark like this, it's open. The modes are setting up, which is why there is a delay. They have started sending. Now the shutter has closed. Let's see why the shutter closed. We'll pause the simulation. As already mentioned, these are the threshold values were already mentioned. In this case, as we see, the humidity has become 95%, which is an adverse condition. In the previous condition, it was all okay. So each of the modes are sending their data. Mode 4, 1, and now mode 4, 3, and mode 1, the central mode has received the information. It says close shutter because it's sensing adverse weather condition at mode 3. Now let's resume with the simulation. Let's see when the LEDs go dark. It goes dark only when all of the modes sense an optimum condition. This will take time for. Okay, let's pause and see why it has become dark. Okay, it says mode 1 says now open shutter because sensing optimum conditions. So let's see the last 5 results of each of the modes. 4 says all of these are in optimum. At 2 also all of these are in optimum range. 3 also all of these are in optimum range. All of these are in optimum range at 1 also. 1, 2, 3, 4. Let's look at 5 also. And here comes 5. We see that it's at optimum condition. So since all of the modes sense its optimum condition, it sends a message to the central mode, and the central mode prints saying that the shutter is open again. Now let's simulate our application 2, smart farming application 2, in the examples folder. We have it stored already. Here is the smart farming .c. We already have these .sky file which is already compiled. For ease of operation, let's take 5 modes only. The code will be shared in GitHub, and you can simulate it up to 20 modes. So the modes are setting up. This will take a little more time because the application is a little big. Okay, here we see that most of the printings are done from mode 1 because we periodically send data from all of these modes to mode 1. and it checks if it's above the threshold. Then it sends a message back to that particular node saying close its shutter. And again, if it senses that it is below the threshold, uh, then it again sends open the shutter. We'll look at an example. For instance, uh, let's look at the case of shutter 5. Send This is mode 1. That mode 1 got a message from mode 5, and these are the values. So as we see, the light intensity has gone above 90 lux, so adverse condition. So mode 1 is sensing it, and it sends a message back to mode 5, close shutter at 5. Now the shutter is closed at 5. Now we have to check the case where we are getting a value from 5 again, mode 5. Here is another value, but as we see, the temperature is above the optimum value, so we can't say to open it again. The next message that we got from 5 is this. We see that all of the conditions are optimum, so we send message to 5 to open shutter at 5. This is all with the simulation part.
We will discuss on the quality of service, where we discuss on the latency and the Contiki versus XMAC. So this slide explains the latency. Latency usually is not that much of a concern since our application is not safety critical. But still, it cannot be tolerated much, because in case of heavy rains or extreme sunlight, the farms and the fields are still need to be protected. We tried different implementations, including the single hop and multi-hop. And these are the graphs that we and the readings that we took from our application. As seen in the single hop implementation, that is the upper graph, it is difficult to predict the time required for the collect data to reach the center node. And this discrepancy can be seen in the graph. And the reason might be that the node is not selecting the optimum path to reach the central node. In the multi-hop communication, it is the one that has been selected for the smart farming system, because in the large field, all the modes cannot be in the range to have a single hop to the central mode. It can be seen from the graph that the average time increases mostly linearly with respect to the number of hops, and thus it can be useful for making an estimate on the time required for the data to reach the central node. Although the single hop architecture has lower communication delay than the multi-hop operation, still the multi-hop operation has been preferred since it is more energy efficient. In this slide, we'll discuss on the Contiki MAC versus the XMAC. The power consumption and the lifetime of nodes is mainly affected by the duty cycle. And the main reason for this is because when the nodes are in the sleep mode, the energy saving will be obviously high. And also the lifetime of nodes will be long if the duty cycle is lower. It can be seen from the figures and the tables that the average duty cycle is reduced for Contiki MAC, which is 3.63%, as compared to the XMAC, that is 9.22%. So it can be deducted that the Contiki MAC implementation is more energy efficient than XMAC. The reasons can be that for XMAC, it first sends a stream of short sized strobes to signal an incoming frame to the receiver. And when the receiver catches one of the strobes, it sends a strobe back. And the sender then stops sending the strobes and starts with the transmitting of the data. But these things are saved in the Contiki MAC, as in the Contiki MAC, to send a single packet, a node will repeatedly just send the full data frame.